So, good evening, students. Let's start this session. We have waited some 8 to 10 minutes for other students to join. So, we will wait for the other in the middle of the course. Okay. So, once again, welcome you all to this live session 11 on 8th of October 2022. So, this live session is of course Physics of Renewable Energy Systems. And this course is taught by Professor Amrish Chandra. He's from Department of Physics, IIT Kharagpur. And this live session is taken up by Rohit, which is me. I'm a research scholar at IIT Bombay. So, uh, according to previous live session, I planned this live session in the same way. Like we will have first the revision of different concepts which we have talked about in previous live session. Then we will go through the old assignment questions. Also in this live session, since this week was very interesting because a, professor talked about characterization and testings of different material using the IR, UV, and X-ray spectroscopy. So I thought that I should also add some interesting things and let you introduce all these things to you in a much easier manner. So I hope this session will be more important for you, even if you want to go for testing or some you want to make career in these fields. Okay, so let's start this session. Let me check if anyone wants to join. Okay, nobody wants to join. So let's start this session. So, what was important for this session was it is not only testing. When you go for research fields, so you ought to have some good some instruments which can give you good results, which can let you identify the functional groups, the particle, the lattices within the matter or atoms, anything. So that's why several instruments were developed based on different principles of diffraction, transmission, emission, Auger electrons. So we'll learn about them in this week 11 session and week 12 session. So these two weeks are very important, I would say. So let's start this session. So if you see the previous session, we have actually covered the nanomaterials. And you know, nanomaterials are very important fields, very important. These are one of the fields which are growing at a very fast pace. And uh, I would say in not only in near future, in the present scenario also, nanomaterials are used on a wide scale. Even we have thinking of nanomaterials in fluids, in refrigerants, in lubricants, in machining oils, in shoes, the material which is made for shoes, the cloths, the army cloths, tanks, aircrafts. Name one field where these nanometers cannot be applied. It can be applied in each and every field. So that's the diverse and beauty of these nanomaterials. Okay, so even we have I see a lot of uh, colleges, universities are actually coming up with courses also on these nanomaterials. So they have especially designed courses for these nanomaterials. So a lot of application for the nanomaterials. So the first thing was that we discussed in the last live session was that what are nanomaterials. So there is a lot of confusion that which material can we call nanomaterial. Is it important to have that material in nano sizes only, or anything that have a regular shape and size but with one dimension in nano 1 to 100 nanometer can be called a nanomaterial. So this is the definition. Nanomaterials are a special class of materials which have any one of the dimension in the range of 1 to 100 nanometer. Okay, so I think we have discussed this a lot in the last class itself, that and these are a special class of materials. These are not like regular or normal class of material that we found in day-to-day activities. Because why special class? Because the properties actually, when you see nanomaterial, the properties are quite different. A stark variation in properties can be seen, and it's what you say. It's quite of interesting for the research community also. Like these nanomaterials were when they were discovered and these properties were actually observed. So scientists were amazed by the properties which nanomaterial can offer to them. Okay, so these nanomaterials are that's why these nanomaterials are one of the widely used materials. Okay, the second thing we talked about was synthesis techniques. Okay, so there can be n number of techniques for synthesis of nanomaterials. Not you can't say there is only a single technique for synthesis of nanomaterials. Depends on the application and your feedstock material from which you want to prepare nanomaterial. There can be n number of ways. So these techniques are actually on a broader term. It can be called approaches. Okay, so we can have two approaches for the synthesis nanomaterial. One is bottom up, in which we take small particles and grow that particle into a nanomaterial. Okay. Another thing is top down. When we take a regular size particle, we break down into the nanomaterials. Okay. So this is the you can say broad difference between bottom up and top down. A lot of difference are there, but in simple terms, this can be taken as a difference. Okay. And in bottom up approach, you see biological methods and chemical methods. These are mostly bottom up approach they take. And the physical, so what do you do in physical? You break these things. You take a big thing, a big chunk, you break that thing by ball milling, laser ablation, or anything. So it's a top down approach. So what is in biological methods? So as the name suggests, biological, bio, it's something which has some life forms. So we use bacteria, fungi, algae, or any other microorganism to prepare these nanomaterials. Okay. Second thing is chemical. So it has something related with chemical things, chemistry. So we have sol-gel technique here, hydrothermal methods here. CVD is chemical vapor deposition method there. A lot of things. These are the important names which I have mentioned here, but there are a lot of techniques. The third one is physical. In physical, we have ball milling, we have laser ablation. Okay, so you know the synthesis techniques, you know the approaches. So I'm pretty sure that when you go to some nanomaterial labs, so you will have a basic introduction of these techniques, and I urge you to visit some nanomaterial labs so you can see these techniques actually getting worked there. You can have a better understanding, visualization also. So that will help you better understand what these techniques are actually. Okay. The third one we talked about is about a great scientist, Richard Feynman, and he's considered as the father of modern nanotechnology. He his lecture was there, in which he said that there is a plenty of room at the bottom, that actually instigated the scientific community to look for sub at not subatomic, I can't call it subatomic, but smaller levels, and they found that really there is a plenty of room at the bottom. You can work a lot on these bottoms, and you can have a wider application of these materials. Okay. The fourth thing we discussed about surface area to volume ratio, where I actually showed you mathematically using these relations that how surface area to volume ratio actually increases for nanomaterials. So if you consider a sphere of a radius r, and what is surface area for a sphere? It's 4 pi r square, and the volume of a sphere is 4 by 3 into pi into r cube. So when you divide the surface area with volume, you get the ratio 3 by r. Okay, so 3 by r. So you see that in this relation, the ratio, the surface area to volume ratio, it's indirectly proportional to r. So when you increase r, that is when you increase the size, this surface area to volume ratio decreases. But when you decrease the size of r radius, like in case of nanometers, you go smaller sizes, like 1 nanometer, 100 nanometer, 50 nanometer, 20 nanometer. So what happens that as you decrease the r, the surface area to volume ratio actually increases. So what is the advantages of increasing the surface area for volume ratio? So in any reaction, if you have a more active sites, it will react more faster. It will have a better reaction rate also. So similar can we think of here also. Like having a more surface area to volume ratio actually offers a great wider range for application. Okay. Now we start the today's lecture. The first question is why KBR? So what is KBR? Let me take a pen also here so I could circle it. KBR. So KBR potassium bromide, okay, and used in FTIR spectroscopy. F here stands for Fourier. So most of you, if you are from graduation degree or maths degree, BSc maths or BTech or physics background also, I think you must have heard about Fourier transformation series, all these things. It's very much similar to that. Fourier transmission, infrared, I is infrared, infra, R for red. So FTIR is spectroscopy. So uh, this is from the previous session. So why? Okay, so why KBR is used in FTIR spectroscopy? So the first thing is, if you are talking about spectroscopy, so it's something optical property. Like how do you get the answer? You look. So if there is a spectroscopy, it's something related with optical properties. You got it? So it doesn't have any low resistance. It is electrical property, cut it. It is thermally conductive. It is thermal property, cut it. It is optically transparent, quite okay. That's why KVR is used, because KVR is optically transparent. It doesn't. Uh, have you seen the slides? And the professor actually explained how samples are prepared, how the samples are covered with KVR. So that's why it's optically transparent. That's why it is used. It is electromagnetically permeable. Okay, so electromagnetic permeability is a quite different thing. It is not used in spectroscopy methods. So the correct answer here is answer C, optically transparent. That's why KBR is used in FTIR spectroscopy. Okay, let me check if someone wants to join. Okay, nobody wants to join. Let's continue. The second question is FTIR spectroscopy can be used in. So first thing, you have to know the application of FTIR spectroscopy. So it can be used in variety of application. So it works on infrared regime. So when you talk about any sample and you want to conduct a FTIR for this, I will talk about it in FTIR in upcoming slides also. I have prepared a specific slide for this because it is so important, FTIR spectroscopy. I want you all guys to know what is FTIR spectroscopy. So when FTIR is actually FTIR, so if you want to detect anything in this sample, it has to be infrared responding. So it must respond to infrared, otherwise you can't detect air. So yeah, it can be used for drug cell interaction. Okay, can also be used for biomolecules, metal complex, nanoparticle interaction. It can also be used for functional group identification. So when I talk about it, functional groups. So what are the functional groups? Like this: ketones, aldehydes, alcohol. Okay, OH group. So FTIR spectroscopy can identify these groups. How? I will show it. Okay, identification of contamination on or in a metal. Yeah, this is also very important application of FTIR. If there is any contamination, it will show in as a wavelength that there is this compound present in this sample. Okay, so the correct answer is answer A is also correct, answer B is also correct, answer C is also correct, answer D is also correct, and answer E is also correct. Okay, so the correct answer for this FTIR spectroscopy can be used in all of these. Okay, now moving to the next question. I think there has been some. So let me tell you a very interesting things about X-rays. Who invented? The question is who invented the X-rays? So X-ray. Why it is called X-ray? This is also a good question. Why X? Okay, why X? And who invented the X-ray? I think most of you have read it in uh, small high school or lower classes also, that X-ray is invented by Wilhelm Conrad Roentgen. Okay, so the correct answer is C. Roentgen invented the X-rays. And not only Roentgen, a lot of people actually worked on the X-rays and developed it. Like Bragg also, I think Crompton also worked, and Lou also worked on it. But it was actually invented by Wilhelm Conrad X-ray. So there is a pretty interesting story. Let me tell you the story also. So what happened that Conrad was actually Wilhelm Conrad was actually working on some fluorescent compounds. Okay, so he actually passed some rays through it just to observe some effect like fluorescent C or some effect. But what happened that these rays actually crossed and have the imprint on a fluorescent plate sample across the sample, and even if he put it in dark room or put the sample in a box and pass these rays, still he obtained a imprint on this fluorescent plate. See, he was quite amazed why it is happening and what are these rays. He was like, these are unknown rays, something X. So X here determines the unknown. Okay, that's why he named it X rays. I don't know these rays, but this can. So he was not very much working on these X rays. He was working on the some fluorescence things or some other things, and accidentally discovered the X-ray. And X-ray has a wide application in medical fields also. For orthopedic surgeons, X-rays are like uh, you say life savior. And X-rays are not only used for this orthopedics or medical field only. It is also used in spectroscopy, studying the materials. There is a whole branch itself which studies using X-rays. Okay, so we have XRD, X-ray diffraction, XRF. We have a lot of things. So that's why X-rays are so important. So you see, in World War I, actually, when he discovered it, he actually got Nobel Prize also in 1901. 1901 or 1902, he got Nobel Prize for this discovery. It was so important. So you can actually see the importance of this X-rays. And actually, this X-rays were used on a large scale in World War I. So a lot of application. It actually developed a lot in during World War I, and in present scenario, you see a lot of application. Still, the application of X-rays are there. We haven't replaced X-rays. We have some other developed methods also, but we still go for X-rays in medical field. Okay, so you can see the importance of these things. And the fourth question is, among the following material, which will be the filter for the Fe? Okay, don't read it as Fe. It's Fe, chemical symbol for iron. So among the following material, which will be the filter for the Fe as anode material for X-ray source? So if Fe is used as a X-ray source, so what happens in X-ray? There is a filter also that actually separates the light, different other lights, and then fluorescent rays. Okay. So which will be the filter for this Fe? So actually there is a list itself that if these are the anode materials, this must be the filter. Okay. So for Fe you see here the filter is Mn. So I've also put the application here, X-ray, how X-ray actually works. So when you put these are X-ray, let's assume these are X-rays, okay, and this is the sample. So what happens when these X-ray actually cross these? We place a photographic plate here. So these X-ray actually crosses this sample and put a latent image here on this photographic plate, fluorescent image. And this image has to be developed using some chemicals which are used to develop these images and studied or read by the experts. So it's not that the X-ray can be operated by or read by anyone. A person has to be skilled enough to read the X-rays. Okay. So, but it has a wide application. It's quite simple. You just have to put the sample there, pass the X-rays, get it on get a latent image on a photographic plate. You develop that plate chemically, and then you read that plate or derive inference from that plate. Okay. Okay, now moving to the question 5. So, what is saying in question 5? We just have to first understand what's the question 5. So, the question 5 says the line broadening in X-ray peaks, okay, can be a convoluted picture of crystallite size T. So, what is the size of crystallite? T effect broadening due to strain. Okay. For a peak at Bragg's angle theta, so there is a Bragg's law. Okay, for these diffraction, Bragg's law for diffraction. So all of these actually was according to this Bragg's law. We will talk about it in later slides also. So you just know that there is a Bragg's law. Okay, for a peak at Bragg's angle theta, the broadening d due to the strain epsilon is given by. So broadening, you will understand when these X-ray actually uh, passes through this. So there is some diffraction there. So that is taken according to Bragg's law, and it is equal to, for X-rays, it is equal to zero point 0.9 lambda upon T cos theta. Okay, here answer is written B. It's D. 0.9 lambda upon T cos theta. Okay, so this is the correct answer. So what is lambda? Lambda is the wavelength of the X-rays. So X-ray doesn't travel in, or any rays doesn't travel in a straight line. It travels like this. So we have this wavelength lambda. Okay, and size of crystallite T, and theta is angle with which it is striking the sample, the atomic planes. Okay, this is theta. We'll read about this theta in Bragg's law when I will tell you about the Bragg's law. And how much is the broadening due to the strain? So if there is a question that this is a broadening due to this crystallite size effect, but how much is broadening due to strain? So this can also be asked in the exam itself. So you just have to remember. So broadening due to strain is 4 epsilon tan theta. Okay. Now moving to the question 6. So you see, this is a very important question. Let me check if anyone wants to join. Somebody's mic is. Okay. So you will see this is a very important, very interesting question, and you will also get to know about how to read these graphs. So I will show you how to understand and read these graphs. So it says a sample is prepared at a different calcination temperature. So you see the calcination temperature RT, RT is room temperature, okay? So generally it is assumed 25 degrees C. 300, 500, 1700. So these are calcination temperature, and the X-ray patterns of those powders are shown below. What can be inferred? So when you see why it is 2 theta, so this is some atomic plane, and the X-ray striking this and getting back. So if this is angle is theta, so it will get diffracted or reflected, scattered with angle theta. So theta plus theta, 2 theta. That's why it is called true. So when you see these graphs, you will see that there is a peak here, a specified peak here at this. If there are any functional groups, it can be understand with this peak can identify it. But not only this, you see that there is a peak, small peak starts growing here, and after here you can't see a peak, but it starts growing here. Here you can't see a peak itself, here you can't see a peak, but at 700 degrees Celsius you are actually seeing a peak. A peak is especially noticeable. 900 peak is there. Okay, so what does this peak actually says? So this peak actually saying that there is a grain growth. You see, there also this peak, the other peak is actually higher than this one. This peak is actually higher than this one. Similarly, so as we increase the temperature, there is a grain growth actually going on. Okay, so the answer A is also correct. As we increase the temperature from here to from there bottom to up, a grain growth is actually seen, and a noticeable grain growth begins at 700 degrees Celsius. You see, here we cannot notice it. There is an increase, but we cannot notice it. It's almost similar. But at 700 degrees Celsius, there is a noticeable grain growth. The grain growth is specified here. You can see the grain growth. So this answer is also correct. All the materials are similar, let us say, with no change in d values. This is wrong because there is a change in d values. We have this nm changing wavelength. This is the nm wavelength, and the data is too noisy to derive any meaningful inference. Data is not noisy. Data is clearly, when you say what is this in noisy data, you can't derive any inference from it. Okay, but here you can derive. There is a clear cut picture that grain growth is happening. A noticeable growth at 700 degrees Celsius is observed. So this is also wrong. This is also wrong. The correct answer is A and answer B. Next question is, when an X-ray beam is incident on a material, which of the following phenomena can take place? So first thing is that the X-ray beam is incident. So this is a sample. X-ray is coming. So what phenomena can take place? Sample damage. If sample is damaged, so how can we use X-ray for spectroscopy? Simple as is some rays are there, so uh, like X-rays. So you have to be very careful when you are using these X-rays because there can be sample damage. Okay, so yes, sample damage can be there, and since these X-rays are actually having X-rays are what? Packets of energy. So they have energy associated, Hc upon lambda energy associated with them. So that energy can actually heat the sample. So this is also there. Scattering is also there. X-ray can be scattered, and photoelectric emission. So this is a very interesting thing. Photoelectric emission. I will talk about it, but photoelectric emission can also take place. Okay, because it has rays has energy. So the correct answer is A, B, C, and D. All of these are correct. And let's talk about photoelectric emission. So this photoelectric emission is actually discovered by a great scientist of this modern era, Professor or Dr. Albert Einstein. Okay, so he discovered this photoelectric effect. When? In 1905. And he got a Nobel Prize for this, for discovering this photoelectric effect. These all these solar cell voltaic solar cells, all these works on this photoelectric emission principle of photo. So what is photoelectric emission? If there is any metal surface and if a ray of beam strikes this metal surface, and this ray of beam has energy E, and this energy E is greater than work function of this metal, that is the energy content of the electron, then electron will be taken out from this surface, and as the rays gets strike, because rays are actually packets of photon which strike the surface, so these electrons can actually emit in a continuum. So this is actually flow of current. What happens when an electron get flow in a path? So it is actually a flow of current. So this is actually a photoelectric effect, and it is very important phenomena discovered by Albert Einstein. So the question 9. Now we are talking about, so all the old assignments question I have finished. Now we will talk about the conceptual questions which I have taken from slides itself. So that your concepts are actually cleared about these things. So the question is, what is diffraction? So you see, diffraction is actually process of bending the light around an obstacle. Okay, so what happens? The light flows like this. So if there is any obstacle, what happens? It will do like this. If the obstacle size is less than the wavelength of light, light will flow like this. If it is uh, more than the wavelength of this light, then what will happen? It will go like this, scattered. So this is actually called diffraction. It has a wide application. Diffraction, X-ray diffraction. We study XRF, electromagnetic diffraction, also ED, all these things. So quite characterization. A lot of work testing of materials is actually done using diffraction techniques. Okay. So next thing is, what is Bragg's law? So when we are talking about this diffraction, the FTIR, not diffraction, I think mainly uh, spectroscopy. So an important law named Bragg's law is actually very much important here, which takes care for these all these things. So you have to understand what is Bragg's law to get an insights about these phenomena. So what is Bragg's law? So when the X-ray is incident onto the crystal surface, I will show it in diagram also in the next case. I will draw it what it means actually. So you can just read the lines. When the X-ray is incident onto the crystal surface, its angle of incidence theta will reflect with the same angle of scattering theta. This is the Bragg's law. And when the path difference d is equal to the whole number n of wavelength lambda, the constructive interference will occur. So there are two types of interference, constructive interference and destructive interference. And for constructive interference, we have 0, 2 lambda, 4 lambda, all these things. And for destructive interference, 0 lambda by 2, 3 lambda by 2, means n plus 1 lambda by 2. Okay. So for constructive interference to occur, uh, this relation has to hold correct. N lambda, where n is the whole number of wavelength, that is 1 lambda, 2 lambda, 3 lambda, and this is d is interplanar difference, path difference between two planes, and 2 sine theta. Okay, theta is angle of incidence. So when you visualize this, assume there are two planes of crystal surface, these two planes, okay, and have interplanar difference of d. So when a light strikes it with theta, will get reflected back with the same angle theta. So when you break this, actually, let's say PQR, okay, draw like this. I think I haven't drawn a straight line. This is a straight line, okay. So draw like this, okay. So this must be theta. So when you solve it, it will be like d sine theta, and also here d sine theta. So it will add up to the 2d sine theta. So for constructive interference, L lambda is equal to 2d sine theta. So this is what is Bragg's law. Now the last thing is I wanted to, this is FTIR result actually. I have actually put it from a research paper itself to show you how FTIR can be pretty useful for its application. Okay, so I wanted that you guys should know how to identify the functional groups using the FTIR and all these things. So the chart on the right hand side is figure on the right hand side is actually a FTIR result of a sample. So FTIR actually measures the transmittance. Okay, this is reflected electron, this is transmitted. So FTIR actually measures the transmitted ray, okay, and intensity basically according to the wave number. So when you see that from here, it goes on increasing. So we have a peak at here 829. We have a peak here. We identify the peaks only. You know, we have just read in Bragg's law constructive interference. So when constructive interference happens, what happens? So it identifies, it is shown as a peak. So there is a peak at 1247. There is a peak at 1508. There is a peak at this. There is a peak at this. Okay. And all these are also peaks. So what is the significance of these peaks? So these peaks actually represent specific functional groups that can be present in this sample. So every functional group has some lattice vibration. So the peaks actually are characteristics of those special functional groups. So when the peaks are in between 2850 to 3330, it so we can infer that there is a CH functional group present. So can you see identify a peak which is in between these and can infer? So yeah, we can here 2930. Okay, so that means that CH functional group is actually present in this sample. The another thing is 1680 to 750, it is C double bond O functional group. So can you identify? Yeah, I think no one, C double bond O functional group. So we can infer that there are no C double O functional group, but there is CH functional group present here. Similarly, C single bond O 1000 to 1300. Yeah, we have 1247. So we can infer that this functional group is present in this sample. So OH is basically alcohols. So you can search for alcohols. Yeah, here you can see alcohols. Alcohol is present. OH bonds are there. OH function group is there, and OH acids. Okay, CH3COOH, like acetic acid. So you will have to look for it. It has a very broad also spectrum, 2500 to 3300. You can look into it. Yeah, this seems to be a acidic functional group 2930. So all you can say that OH acid, OH alcohol, C2H5OH. Okay. So all alcohols have OH functional group, C2H5OH, ethanol acid, CH3 COOH is acetic acid, CO this functional group is also there. This is not there. Okay, we didn't find any in this functional group, so this is not there, but this is there. So we can say that these functional group are present there using this FTIR spectroscopy graph. So that's why it is important. We can identify the constituent functional groups. We can also identify the different adulterants in the uh, this sample. So that's why it is very important to know about these techniques. These techniques are actually worked on, used on a wide scale in research universities, in research labs. So these are actually foundational basics of characterization. And also, when you go for a speciation study like heavy metals, toxicity, leaching, so you can use these instruments. There is AES also based on auger electrons. So a lot of things, a lot of other instruments you will characterization technique you will also read in the last week lecture, week 12. But till now we have read about these diffraction based methods, the FTIR, the XRD. So these are quite important for its application. Okay. So let me do a quick recap also for those who joined late. So we talked about the revision of previous live session. So we talked about what are nanomaterials, what are the different synthesis techniques like biological methods. We talked about chemical methods. We talked about physical methods. And we talked about the great scientist Richard Feynman and his very important and very directionful lecture. There is plenty of room at the bottom. Also, we talked about how surface area to volume ratio can impact the properties, and then we talked about the FTIR, why KBr, potassium bromate is actually used. Then where FTIR can be used. So FTIR can have wide range of application, including drug cell interaction, biomolecules, metal complex, nanoparticle interaction, functional group identification, like we see in the last slides, identification contamination in a metal. Then we talked about who invented the X-rays. Then we got to know about how X-rays were discovered. Then we talked about what are the filters for different materials. So these are the filters and how X-rays are actually utilized for characterization. Then this is just a simple conceptual based question in which you have to learn about what can be the broadening due to strain or broadening due to this crystallized size effect. Also a sample, we talked about this graph or figure, and then we drew inference from this figure, like there is a noticeable grain growth at 700 degrees Celsius senior, and grain growth actually increases with increasing temperature. Then we talked about sample X-ray beam incident and which phenomena can take place. So yeah, all of these can take place. Then we talked about diffraction, and then Bragg's law, which is a very important law in these characterization instruments. Then we actually took a live example in which we studied the sample with FTIR and identified the functional groups, know the technique how it can be used to identify the functional groups present in the sample. So this with this I conclude this live session. So thank you all for attending this live session. You are always welcome to ask your queries, and you can always find me at this email ID. If you have any queries, you can write me up in this email ID, and There is a discussion forum also in the NPTEL. Also, I post these lectures. All the lecture videos are actually posted on my channel also. So there is when you go to NPTEL, you will see that there is a problem solving session tab there. So click on it. You will get the links. So I put the links there. I upload these videos in YouTube. So if anybody wants to go through these videos again, and or if you want to, if someone who has not attended the live session want to know or learn about it, so he can always click the link and go through it. I also put these slides there, so these can also help in preparing for your end exams also. Okay, so I request you all to go through this problem solving session, click that tab and go through these links. Okay, and you will see a week wise link there. So my colleague Ravi also put his link there, so you can go through any of us videos. We cover different assignment questions, so I would suggest that you would see all those links and go through all those links. Okay, so once again, thank you all for attending this live session. It was very interesting. So if there are any queries, you are always welcome to ask it now, or you can always ask in the different discussion forum where everyone can be benefited. So see you all guys in next live session, which will be, I think, the last live session of this course. So thank you all. Uh, yes. Mm-hmm. Uh, can you repeat? I can't clearly hear you. So there is an atom, and you see X-ray going through it, and it is diffracted. Uh-huh. Mm-hmm. Mm-hmm. So you want to say that this X-ray is actually going and it is actually striking and get diffracted. So is there any relation between these? Yeah, there are relations. Yes, there are a lot of relations. Uh, many researchers have actually worked on these relations, and I think based on Miller indices also you can draw some inference also. Because I am not very much into this field, but I have seen the relations. Mainly physics background people actually work on these, and I would surely say that with confidence that there are relations present which actually trace the path of these X-rays. Okay. Uh-huh. Mm. Yes. Mm-hmm. See, what happens? These exams are set by the professor himself. So he has actually he must have submitted these questions before the course itself. So that's how these courses are actually designed. So I don't know much about it because I am a teaching assistant. I am not the professor himself. But I can assure you that the questions are basically conceptual. It is not like you apply. We promote a lot of use of formulas, but it's on the same time. I would suggest that the important formulas you should learn it. Okay. Huh. But most of the question, even in the assignments itself, you will see that most of the questions are basically conceptual. They are not formula based. Very less of them are actually formula based, which I have explained here also, like in capacitance method or supercapacitor when I was talking. So yeah, there are formulas like when you do the area IDT and calculate the self potential. So these are some important formulas which we will have to remember, because when we'll have to calculate the cell potential, so we know how to calculate these areas. We have to know how the calculate gives energy, gives free energy. So yeah, I would count that at most you will have to remember some at most 7 to 8 formulas. That's all. Okay, okay, okay. Welcome. Sure, sure, sure. This is always encouraged from the NPTEL also, because in discussion forum, lots of people can actually benefits from the doubt. Like you have asked about this equation, how to trace the path. Yeah, there are equations. I have actually seen them. I have not used them, but I have seen these equations. So yeah, uh, always encouraged. Okay, welcome. So, with this, if there are any questions, you can students, you can always ask now itself. I am here only. If there are no questions, then I think we should end this session, and then we again meet at 15th October. So for live session 12.